Okay, so today we'll go to the next topic of this uh, constraint optimization numerical method. So we are going to look at this augmented Lagrangian method. So this augmented Lagrangian method is a fully computerized method. Okay, fully computerized method. It does not require any manual input, and also it is based on the penalty function approach. So we already studied the basic penalty function approach where the user has to do everything. The user has to give different values of R1, R2, R3, etc. And he has to check for convergence and all. But in this augmented Lagrangian method, it is fully automatic. And this augmented Lagrangian method is supposed to be used in some packages like ANSYS and all that to do the weight minimization and things like that. So this method is very complicated. So we only look at the implementation. Okay, it will not be asked for exam because it is based on penalty function approach. We'll see how penalty function approach is implemented in a fully automatic manner. Okay, so it will have some scaling factors R, and it will have two things, sigma and tau, which will actually become equal to the Lagrange multipliers, and they are found iteratively using the update rules, and these are based on constraint violations. So there's no need to put switching conditions or to calculate R1, R2, etc. manually. So it is used by many CAE packages for optimization. Okay, so just to see how it is implemented, we are going to look at it briefly. Okay, so suppose you want to do the minimization of f of x, and two constraints are there. Okay, one inequality constraint, one equality constraint. So inequality constraint must be written in the form g of x is greater than or equal to 0. Equality constraint will be of course equal to 0. So the augmented Lagrangian function is written like this. So this is our objective function plus R1, a scaling factor for inequality constraint, multiplied this penalty term. Okay, then R2, scaling factor for equality constraint multiplied by this penalty term. Okay, so here, okay, the same thing is repeated here. Here R1 and R2 are scaling factors which converge at large values of R, and they are held constant in one set of iterations. And if the result is not satisfactory, next iteration with higher values of R1 and R2 is tried. So here the algorithm itself will give like this. Okay, R1 equal to 0, R2 R2 is equal to 0 first. Then it will do some iterations. If that doesn't work, it will put R1 equal to 1, R2 equal to 1. And if that doesn't work, it will put R1 equal to 10, R2 is equal to 10. Okay. So it will automatically change values of R1 and R2 without any user input. Okay. Then what is this thing here? Okay. So this is actually g of x in the bracket. It's a bracket operator penalty function for the inequality constraint. So what is the meaning of bracket operator? It means that if g of x is negative, that is there is a constraint violation, its absolute value is taken. And if g of x is positive, then you give 0 here. Okay. So that is the value of bracket operator. So what is this thing here? This is the parabolic penalty function for equality constraint. So the value of h of x is put here. So if h of x is equal to 0, that is the equality constraint is fully satisfied, then the value of 0 will come here. Okay. So these are the penalty functions. Okay. Okay, then what are these values? Sigma and tau. So sigma is a number which can be shown to be proportional to the Lagrange multiplier u at convergence of the sigma. We earlier studied that u is the Lagrange multiplier used for inequality constraint, and V is the Lagrange multiplier used for equality constraint. So this tau can be shown to be proportional to Lagrange multiplier nu. Okay, nu or V, okay, whatever it is. So that is the significance of sigma and tau. So how do you give values of sigma and tau? So for every iteration of R1 and R2, sigma and tau are updated in sub-iterations. Okay, so what is the way method of obtaining the value of sigma and tau? So initially, sigma 1 and tau 1 are taken as 0. So this is taken as 0 first, initially. Then the next value of sigma, that is sigma t plus 1 is equal to this inequality constraint, that absolute value of the inequality constraint plus previous value of sigma. Then the next value of tau is equal to the equality constraint violation plus the previous value of tau. So it is seen that for every iteration of R1 and R2, sigma and tau are updated like this. Okay, until sigma and tau converges. If they don't convert, you go to next value of R1 and R2. So that is described here. Okay, brief summary of the algorithm. So initially R's are given small starting value like 0.1, 1, 10, 100, etc. So R's are kept constant for one stage of iterations as below. Okay, then sigma and tau are giving starting values of 0 at every sub iterations, and you have to see if this augmented Lagrangian function is properly minimized with these the values of sigma and tau. And with those constraint violations we can update sigma and tau. And if the convergence is unsatisfactory, the whole process is started with new values of R1 and R2. So it is like this. So first you put R1.1, R2.1. Okay. Then you put various values of sigma 1, tau 1, sigma 1, 2, tau 2, sigma 3, tau 3, etc. Okay. So the objective function not converging, then you stop this iterations, you repeat everything with R1 equal to 1 and R2 equal to 1. So in this case also, you have to start with sigma 1 tau 1, sigma 2 tau 2, etc. and see if the solution is converging. So if still that does not converge, you put R1 equal to 10, R2 equal to 10, then try various values of sigma 1 tau 1, sigma 2 tau 2, sigma 3 tau 3, etc. And at one value of R, say 100 or 1000 or something, the whole thing will converge and you can stop the iteration. So this is the basic of the augmented Lagrangian optimization method, which is used in many professional CAD packages. Okay, so we can stop this with this. So these are all checks for convergence. Okay, so at convergence, this A must be equal to F. A of x must be equal to f of x. So the penalty term must vanish. Penalty terms must vanish. Okay. Then the constraint violations must be nil. Then sigma and tau must convert to a constant value. Then this derivatives, partial a by partial x and all should be equal to 0. So we can stop here. So next we look at this toolbox. Okay. MATLAB toolbox, we did only for unconstrained problems. Okay. We only looked at unconstrained optimization. So now we look at constrained optimization before we do the next assignment. Okay. Okay, so we start with this quadratic programming, how it is done in the MATLAB. Okay. So we already studied the theory of quadratic programming. So what you do is that the objective function is approximated to this quadratic form. Okay. And this del squared f is actually q, and this partial f by partial x, partial f by partial y is equal to this this del f matrix. Okay, this del f matrix or Hessian matrix. So in this subroutine for quadratic programming, the user has to calculate this first derivative matrix and second derivative matrix. Actually, the value of q and f can be automatically calculated by using other MATLAB subroutines. Okay, but whatever be the case, if you want to use this quadratic programming subroutine, you have to find this first derivative matrix and second derivative matrix at the value of x0, y0, which is given to you. Okay, so and also you need to specify the a set of equality and inequality constraints. That is, linearized equality and inequality constraints must be given in this form. Okay, so A equality is the right hand side of the, is the left hand side of the equality constraint matrix, and B equality is the right hand side. So this D is actually D1, D2. Okay. Then similarly for inequality constraints, A is the right left hand side of the inequality constraint matrix, and it contains all the coefficients, and B is the right hand side. So in order to call this quadprog subroutines, the arguments are first q, that is this q matrix is first q, then this second derivative matrix must be supplied, then A, B are the inequality constraints, A equality, B equality are the equality constraints, LB, UB are the lower bound and upper bound of D1, D2, then X0 is the starting point of the D1, D2, and the options are set by OptimSet. So luckily we have already solved this problem in the quadratic programming lecture. So I will repeat it and see if we get the same answer. So this was our original lecture question. So we already calculated first derivative matrix. We already calculated second derivative matrix. Okay, sorry, one phone call was okay. So this F matrix and Q matrix we are calculating anyway. Okay, then the constraints has to be converted to linear form and then expressed in the D1, D2 form. Okay, so this xy minus 2 is the equality constraint. In the non-linear form, it is converted to the D1, D2 form after linearization. So we get the coefficient matrix A. So the terms are 1 and 2, and then the right hand side is 0. You can see it is 0. Okay, then the next constraint is x plus y is equal to 1, which is already linear. So you have to write it in the D1, D2 form. So then the coefficient of A is minus 1, minus 1, and the coefficient of B is 2. Okay, so all the terms are obtained. Okay, so now you can see implementation of this subroutine. So first you have to do optims equal to optim set pod prog to set the default value. Then the F matrix is defined. Okay, then the Q matrix is defined. Then equality constraint coefficient matrix, right hand side of equality constraint matrix, then inequality constraint coefficient matrix, right hand side of inequality constraint. Then the starting point is 2, 1. Then we don't know the lower bound, it is set to null. We don't know the upper bound, it is set to null. And then this program is called. And then if you ask it to type it the value of x, okay, then it will give the values of D1, D2, which is exactly what we got in the lecture notes. Okay, so this is only one iteration of the quadratic programming. So next, the next iteration will start with these values of D1, D2. It has to be converted to x1, y1 and must be converted to quadratic form. Okay, quadratic form, and the new values of f and q has to be found and substituted in the subroutine again. Okay. Anyway, this quadratic programming method is very complicated, so we will go to the easier method which many people use. Okay. Okay. This one, general constraint optimizations using linear and non-linear constraints. So this is a very useful subroutine for practicing engineers. Okay. So how does this work? So F minimum constraint. Okay, that is the name of this subroutine. Then okay, so A equality, B equality represents the coefficient of linear equality and inequality constraints. So A equality, B equality. That is the linear equality and inequality constraints. Then fun is the definition of the objective function. We already studied how to give. So if fun is written in apostrophes, it means that you have to write it in a separate file called fun.tm. Okay, so fun is not given in apostrophes here. It means that it is written as a 1 or 2 line function in the main code itself. Okay. Okay, then okay, LB, UB is the lower bound and upper bound. The non-linear cone. Non-linear cone is the function or a subroutine which is separately written in a .m file which specifies the non-linear constraints. Okay. So terms having x squared, xy or sin x, cos x, etc., which are not linear, so they cannot be put into A equality, B equality, etc., because they are non-linear. So you have to open a file called non-nlcon.m and you have to specify all your non-linear constraints. Okay. So let us see how it looks like. So this is the format of that file. So that first line should say like this. That is C, and C equality is equal to this non-linear con.x. So the values of x, that is x1, y1, etc., are substituted here by the main program, and this C and C equality will be returned back to the main program. So what is there in C and C equality? So the C equality will store the value of the equality constraint. Okay. Okay. So if we store the value of the result of the equality constraint when you substitute this x1, y1. So if the C equality equal to 0 means equality constraint is satisfied. But if C equality is 1 or minus 1 or 2 or 4, it means that equality constraint is not satisfied. So when this value is sent back to the main program, it will know that this equality constraint is not satisfied. Okay, then what about the value of C? The value of the inequality constraint is stored in C. So inequality constraint must be specified as g of x is less than 0. Okay, so if the C has values like say -1, -2, -3, etc., it means that equality constraint is satisfied. So if C returns values like 2, 3, 4, etc., it means that it is positive values. And when this value is returned to the main calling program, it will know that the inequality constraint is violated. So by checking the value of the C and C equality, the main program will know that if the nonlinear constraints are violated or not. Okay, so first we'll use this as a simple example. Minimize this cubic objective function having three variables, x1, x2, x3, subject to this nonlinear inequalities. Okay, and there is no nonlinear equalities. Okay, and then there is some linear inequalities. Okay, so how to solve these things? Actually, this is actually variable bounds. Okay, there's no need to actually variable bounds. Okay, so there's no need to write as the linear inequalities, but we can do this also. Okay. Okay, so this says that x3 variable x3 should be less than or equal to 5, and this says that the minus of x1 or x2 or x3 should be less than or equal to 0, or x1 or x2 and x3 should be greater than or equal to 0. Okay. Okay. Okay, so x3 should be between 0 to 5, x2 should be greater than or equal to 0, x1 should be greater than or equal to 0. So this is the meaning of all these things. Okay. Actually, this can be represented by variable bounds. Okay, so how do you write the nonlinear constraint file? So you open a file called nonlinear_con.m and you type in the definition of the first nonlinear inequality constraint and second nonlinear inequality constraint. So that is C. Then no nonlinear equality constraint. Okay, so C equality is set to none. Okay, so if you look at this vector C, it will have C1 and C2. Okay, so this is actually C1, this is C2. So C1 will store the value of G1 and C2 will store the value of G2. Okay, and these values will be sent back to the main program. Send back to the main program. Okay. And then linear constraints. Okay, so actually this variable bounds is written here as a linear constraint. Okay, that is also possible, but that is not required. Okay, let us see and understand. Okay, so this says that this is x3 is less than or equal to 5. Okay, minus x1 is less than or equal to 0. Minus x2 less than or equal to 0. Minus x3 less than or equal to 0. Okay, so same thing can be written with lower bound and upper bound. Okay, so this is actually a unnecessary complication. Oh, but this will also work. And then there is no linear equality constraint and inequality constraint. So it is set to null. And then definition of objective function is typed in this fun.x or fun.m file. Fun.m file. So all these things have to be done first. So after that, we will execute the program. So first is you have to type optim set of options equal to optim set f minimum constraint. So this will set the default tolerances and number of iterations and all for this subroutine. And starting value of x1, x2, x3. So x1 is 1, x2 is 1.3, x3 is equal to 0. These are the starting values. So these are the constraint values. Okay, then lower bound, upper bound we are putting to null. Okay, because we already indirectly gave lower bound and upper bound in this statement. So there's no need to duplicate it. Okay. Then then next you execute the subroutine by typing this statement: if minimum constraint and fun, that is the name of the objective function, starting value of x1, x2, x3, then a equality, b equality, then lower bound, upper bound values, then nonlinear constraint. So once the function is executed, okay, the answers are stored in X. Then if you just type X and press return, it will show the values of X1, X2, X3 stored in the X. So these are the answers. So what you can do is that after getting these answers, X1, X2, X3, you can see if the constraints are not violated. So what you have to do is that you can type this statement and press return, and you can see the values of C and C equality. So all the C values must be positive and C equality must be 0 at the end of the run. So this is just a theoretical example. So next we look at a machine design problem from S.S. Rao's text. Okay. So actually this optimization example with the MATLAB toolbox was done by S.S. Rao himself when he visited IIT Madras, and I got a copy of the solution. So basically you can see that a metal piece A is welded to a block B, and the purpose of this optimization is to minimize the volume of this weld area. Okay, minimize the objective is to minimize the volume of the weld area. Okay, so let me erase everything. Okay, so what are the optimization variables? Four optimization variables are there: H, L, T, B. So H is actually called the, I think it's called the leg of the weld. Okay, leg of the weld. Okay, because I am teaching machine design, I know these terms. Okay, leg and throat, two types of things are there. So suppose uh, this is a welder. This thing is called throat. Okay, the diagonal distance is called throat and represented by A, and these two are leg or leg. Okay, okay. So the H is leg of the weld. Then the B is the what to say, the width of this beam. Then T is the depth of the beam. Then L is the overhanging part of the beam. Okay, so those four things are the design parameters, and this is the expression of the objective function, which is actually, I think, the volume of the weld material. So this has to be minimized. Has to be minimized. Okay. Okay, then it has 7 inequality constraint. Okay, so the first inequality constraint says that tau of x, that is the shear stress in the weld, must be less than the allowable shear stress for that weld material. The next this sigma x is the normal stress in the weld, must be less than the allowable normal stress in the weld. Then another is x1 minus x4 is less than 0. Okay, let us see what is the meaning. X1 minus x4 is less than or equal to 0. Okay, so I think I understand. So x1 is h. Okay, x1 is h. So this is also h. X4 is b. Okay, so what it is saying is that, so this is b. So this breadth, width is b. Okay, and this leg of the weld is h. So yeah, H should be less than or equal to B. Okay. So that is the meaning of this x1 minus x4 is less than or equal to 0. Okay. Then this probably means that delta x, that is the tip deflection of the beam, must be less than the allowable tip deflection of the beam. So these are some various constraints. Okay. Then four variable bounds are there. Okay. That is x1, okay, xi, I equal to 1, 4. So x1, x4 are they varying from 0.1 to 2.0. Okay, x1 and x4 are varying between 0.1 and 2. Okay, then x2 and x3 are varying between 0.1 and 10. x2, 0.1 less than x3, less than 10. That is the meaning of this. Okay. So this has to be given to variable bounds. And these are the various definitions of the terms used. So this is the normal stress. This is the tip deflection. This is the shear stress. This seems to be the bending moment. This seems to be polar movement of inertia, and so on and so forth. Okay, so first open a file called fun.tum and type the definition of the objective function here. Okay, so when you supply x1, x2, x3, x4 in this fun.x, it will return the value of f back to the main program. Okay, then you have to open a file called non-nlcon.m, and there you have to type all these things. Okay, so this is the value of force, Young's modulus G. S max is the maximum shear stress. S max is the maximum normal stress. Delta max is maximum tip deflection. Then maximum shear stress. So 7 constraints are there, it seems. Okay, 7 inequality constraints. This is the first inequality constraint. That is tau minus shear max. Okay, that should be less than or equal to 0. S minus x max, or normal stress minus maximum normal shear stress. Then this is that H is less than or equal to B. Then all these things. Okay, so if you take C will have 7 values: C1, C2, C3 up to C7. So C1 will contain the result of this inequality constraint, first inequality constraint. C2 will contain the result of the second inequality constraint. C3 will contain the result of this third inequality constraint. So all these values should be positive in the end. Okay. Otherwise, it is constraint violation. Okay, so now you can execute this code. Okay, so first you type optims equal to options equal to optim set f minimum con. This is the starting value of the iterations. Okay, the starting value has been taken from SS Rao's lecture. How we got it, I don't know, but if it is not there, by trial and error, you have to find a value of x1, x2, x3, which is in the feasible range. Then lower bound, upper bound. Okay. Then you call this f minimum constraint subroutine. Okay. So f fun is the name of the objective function subroutine. The nonlinear con dot m is the name of the nonlinear constraint subroutine. X0 is the starting point. So there is no equality constraint. So A, B, A equality, B equality is all 0. Okay, so after you execute this, then all the answers will be stored in this. So in this X, all this X1, X2, X3, X4 will be stored in this X. So if you type X and press return, all the four values are stored here. Okay, X1, X2, X3, X4. And this is the value of the objective functions. So now you have to check if these are violating any constraints. So what you have to do is that you type this line at the end of the program and you press return, and it will show the values of C. When this is C1, C2, C3 up to C7. Okay, so you can see that all the constraint values are less than or equal to 0. Is it less than or equal to 0 or greater than or equal to 0? Let us look at this. It should be okay. Let us see. Okay, so it is right. It should be less than or equal to 0. Earlier I mistakenly said it should be greater than or equal to 0. Okay, it should be less than or equal to 0. Okay. Okay, so this is the final check. Okay, final check for the constraint violations. And I think with that we can stop. Okay, so next topic we'll study this genetic algorithm. So you can do same thing with genetic algorithm instead of this previous method. So this method which we just studied, okay, so this subroutine which we just studied, it uses some calculus based method. Okay, calculus based method. Okay, so like some Cauchy's method or some other thing. Okay, combined with maybe some sort of penalty function, which we don't know. So this method is good if there is if the problem is convex. So the objective function is convex and feasible region is convex. Okay, so then this subroutine will work very well. Otherwise, if it is non-convex, we have to use this genetic algorithm. Okay, so which we'll study later. So we can stop here. So with this, I think I'll give the second assignment. So second assignment, you cannot solve immediately because topics like genetic algorithm and multi-objective optimizations is included in the second assignment. So, but you can start doing the second assignment little by little. And when I teach genetic algorithm, you can solve that part also. Okay. So we can stop now.